All right, I am going to get started. I want to introduce myself. My name is Christine Maceo, and I am coming to you from the STEM Center for Education and Outreach at the United States Naval Academy in Annapolis, Maryland. And I'd like to participate in this educator workshop this week. Every day from 3:30 to 4:30 your time, a different STEM topic specifically focused on high-tech STEM areas of algorithms, computer science, math, physics, and engineering. And so tonight's session will be on computer programming, specifically if statements and Boolean operators. And the worksheet that went along with this activity, I'll highlight it right now, looked like this. So I had asked you to make several copies of this sheet and then to cut out along the dotted line here and to cut out each of those little boxes up there, because we are going to do a hands-on if statement exercise with that short. Okay, so let me get rid of this. And what we're really going to be focusing on tonight is or today for you, for me it's night, for you it's day. So what we're going to be focusing on today is going to be decision-making algorithms and Boolean operators. And so I have up here on the screen, or I will have a decision-making tree just to show you or demonstrate for you what the decision-making process looks like. You do it every day, you do it all day, but you might not actually think about it. And so this is specifically a decision tree for what kind of pet is right for you. And I know that you're virtual and we can't really interact, so I'm going to answer these questions for you, but I want to show you a little bit about the decision-making process and what you might think about if you were possibly considering getting a pet. All right, so what kind of pet is right for you is the first question. And then we're going to go down level by level, and we're going to just ask a little bit more detailed questions in order to narrow in or zero in on this pet, narrow down the pet choices. So do you want a pet? Of course, that's the first question you would ask yourself if you're starting to think about getting a pet, is do you want a pet to love and care for? So the answer to that, these are all yes, no questions. Do you want a pet or do you not want a pet? So I am going to say that I do want a pet. So I'm going to come over here and I am going to write yes. The other option was no. And I'm not going to go down that branch of the tree. All right, so we have determined that I do want a pet. The next question is, are you likely to remember daily that you have a pet? Because if you're not going to remember every day that you have to feed and walk and water a pet, it might limit some of your choices. So I actually am going to say, yes, I will remember every day that I have a pet. So again, the other answer was no. And I'm not going to go down that branch. We'll move down a little bit further. Do you want a pet that returns your love? So that means, do you want to give your pet attention? So some pets are just there and some pets require daily attention. Yeah, it's something to think about. How much time do you want to put into that pet? I also just want to point out that if I had answered no to are you likely to remember daily that you have a pet, I would then go straight to will you remember occasionally that you have a pet? But we're not going down that trail. Going down this one right here, this one right here. All right, so I do want a pet that returns my love. I want to interact with this pet. So we're going to go again with yes. And the other answer again was no. All right. So now we're getting to the nitty gritty. I've decided I want a pet. I've decided will remember I have a pet, and I've decided every day that I want to interact with this pet. There's another question now. So do I want to train my pet? So do I want to spend time with it and make sure that it can behave? And I think I will hear actually say no. The other answer was yes, but I'm going to say no to this. All right, so we're going to continue down this way. And no leads us, do you own a large yard? So I'm not going to train my pet. So I guess the idea is that maybe it would stay outside. So I live in the city, so I'm going to say no. Again, the other answer was yes, but I'm going to head down this way. And it pointed me to a hamster. So I answered those yes or no questions. It was put together for me in a branch. It led me down different branches. It got more specific as time went on. And then based on my answers, this little diagram made a decision for me. So if I had answered yes, 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 no, no, it was going to give me a hamster. If I had lied for any of those answers, it was still going to lead me to the answer of a hamster. It just would have been the wrong pet for my actual situation. So that's what I wanted to point out today. The decision making, yes and no, true or false, all of those don't have any thought process. So if you're going to not be truthful, then it's going to give you the wrong answer. So we're going to look a little bit more into that today. And we're going to specifically look at the idea of Boolean operators. Any questions or comments before we move on to that? Okay. So this is going to be just a little bit of background information for the actual activity I had planned today, which is going to be coding and doing a little bit of computer programming. But before we do that, there's something I want to discuss in terms of Boolean operators. And Boolean operators are actually a lot like that decision-making tree that we just looked at. Boolean operators have two states, and they can be called different things, but there's only two of them. Sometimes they're called 1 and 0. Sometimes they're called yes and no, which is what we just saw. Sometimes they're called on and off. And sometimes they're called true and false. So what Boolean operators do is they take these two states and they make decisions based on them. So you can think of it as a box because there's different Boolean operators. And it's got input. And it's got output. Sometimes it has more than one input. So I'll put 2 here. There could be more. And there's some kind of operator in here. And again, like I said, there's multiple different operators that we are actually going to look, that there are. We're going to look at 3 of them today. But basically, these Boolean operators, logic gates, decision-making devices, take a look at what comes in, the state of what comes in. By that, I mean 1, 0, yes, no, on, off, true, false. Makes a decision that it was built to make. So again, it doesn't matter if the signals coming in were right or wrong. It's going to make the same decision, and that also is going to be on or off, yes or no, true or false, 1 or 0. So we're going to look at 3 specific ones that the simplest ones actually that go in here, and they are called not and or. And I guess I should ask before I go any further, are there any questions? Feel free to put any questions that you have in the chat and I'll be happy to answer them. Okay. All right, so we are going to look at the not operator first, and the not operator changes the state or changes the truth or changes the signal from on to off. So it takes one signal in. So this is an example of a logic gate or an operator that has one input. This time we know that that operator is called not, and it makes one output. And when it does, it changes the state. What that means is if I put a 1 in for the not gate, I get a 0 out. If I put a 0 into the out gate, not gate, I get a 1 out. So that's all it does. It says, I know what you are, and now you're this, and it changes what it is. A lot of times these gates, operations, are represented in what we call a truth table. And I'm going to show you what the truth table looks like for the not gate. First of all, the input is called X. So I'm going to make a table that has X as an input. So X is leftmost. And what I said is that the input can have one of two different states. So the only options for X are 1 and 0. And this is my input column. And then I have an output column on this truth table. And usually that output column is represented with a logical symbol. For not, it's a little dash on top of the X. So for the input 1, if I apply the not operation, I get a 0. For the input 0, if I apply the not operation, I get a 1. And that's the truth table for that. And that's a simple logic gate, simple operator with one input and one output. Any questions to put in the chat for that? Okay. Then I'm going to move on to the other two gates. Now these are compound gates. And the first one we're going to look at is the AND gate. And by definition, an AND gate or an AND operator is on only if the two inputs are on. So this is different with the AND gate in that there's two inputs. And again, this is the rule, or this is how AND is defined. If two inputs are on, then it outputs an on. So this will look a little bit different as a diagram in that I will have an input 1 or an input A and an input B and a single output. And again, anytime I see this AND, it's going to make the same decision for me, whether these two inputs were correct or not. So it's a little bit more difficult to write all the possibilities next to the two inputs here and all of the outputs for those possibilities. So that's really where the truth table comes into play and becomes useful. So I'm going to show you what the truth table looks like for the AND gate. First of all, I have two inputs, X and Y. This would be input A, and this would be input B. And then I have an output in the third row. So if I look, and remember, Boolean can have only two states, that's 1 and 0, but I've got two separate inputs here. So actually I have 4 different possible combinations for this. I have 0, 0, 0, 1, 1, 0, and 1, 1. So these are the 4 possible combinations for those inputs. And if we take a look at the different definition of AND, I'm going to get an on output only if the two inputs are on. So this bottom row right here is the only place where that happens. So that's the only place I'm going to get an output that's a 1 from an AND gate. Every other time, I will get one that's off. Now I represent the AND. I have to include both of my inputs. And then this is with a little x. So usually in a circle to distinguish it from the x variable. So that's what the and truth table looks like. Any questions about that before I move on to the or? All right, so then we'll do our last one. Look at the OR gates. And OR, by definition, is on or has an on output if one or more inputs are on. So again, this is going to be some kind of gate that takes we'll do two inputs, input A and input B, and has an output. So I still, in my truth table, am going to have an X and a Y. And I'm still going to look at all four of those combinations that I possibly can get for the input to that gate. And then I'm going to try and figure out, well, what would this output look like based on this definition up here, which is that OR is on if one or more inputs are on. Well, what that means is that any time one of my inputs is on, which it's in 3 cases this time, I'm going to get an on for an output. The only time it will be off is when both inputs are off. Again, I need a symbol to represent that. That's usually a plus or a plus with a circle behind it. So those are the truth tables. Those are the logical operators. They're used in computer programming all the time. Just for this reason, they're used in electronics too, but we're going to specifically look at their use in computer programming, and they are 1 for true and 0 for false. Any questions about that? All right. Then we're going to move on to our computer programming part now that you know about Boolean truths. And before we do that, we're going to talk a little bit. I'm going to focus today on if statements. So in computer programming, a lot of times what we think about is the different languages that we program in. And all of those programming languages have their own syntax, and they have their own way of actually writing the computer code, but they do have basic principles that are common throughout. And so we're going to look at if statements. We're going to look first in a very unplugged way, and then at the end we will start taking a look at how you might program using some of these if statements. Anyway, if statements have a very specific format, and they start with the word if, first of all. And usually after the word if, there's usually some kind of Boolean expression. And that Boolean expression is evaluated, or its truth is determined. And if that Boolean expression is true, then you enter the if statement and you perform an action. Something that the computer program is going to do if this condition, this Boolean expression, is met. If you put something into this Boolean expression and you do not get a true value, then you don't execute that action. So that's the simplest type of if statement. So if the light is green, drive, go. If the light is green, you look up, and if the traffic light is green, then you drive. If it's not, you don't enter this at all. You certainly don't drive. Okay, so that's the simplest type. Sometimes there's another statement after that. It still starts with a Boolean expression. And if that Boolean expression is true, you're still going to execute an action. This time I'm going to call it action 1. Else, meaning if that Boolean expression is not true, I'm giving you another action to execute. So else, execute action 2. So if the light is green, go. Else, stop. I told you what to do if the light was not green. That's the second simplest if statement. We'll look at one more, and this is what we're going to concentrate on today, nested if statements. So I'll put a star next to this. Talk about nested if statements. All right, so they start the same way. If some Boolean expression is true, execute action 1. Now in the previous example, I said else execute action 2. This time I'm going to use a different word, else if Boolean expression 2 is true. Execute action 2. So this time I didn't just give you another statement to execute if you couldn't do the first one. I actually gave you a second conditional that was stuck in here before I gave you that action to execute. And I could have another else down here, else execute action 1 or action 3. So as these if statements get nested, what we're going to investigate today is what happens. Does the order matter when you nest if statements? What happens to the output, or what does your algorithm do based on these if statements? So before we go on to an actual example with all of our cut numbers, I wanted to see if anybody had any questions. You can feel free to put it in the chat. I'm happy to answer. All right. So then what we're going to do is I'm going to ask you to take out your first set of cut numbers and your first set of little bins. So bin A, bin B, and bin C. And then your numbers 0 through 19. And what we're going to do is we're going to use nested if statements to sort these numbers into bin A, B, and C. And I'm going to write the if statement right here that we're going to use, or the nested if statements right here that we're going to use in order to sort these numbers. All right. So we are going to say if the number is even, meaning divisible by 2, place in bin A. Else if the number is odd, place in bin B. Else, place in bin C. Those are our nested if statements that we are going to use to sort numbers into these bins. All right, so we're going to leave this up here, and we're going to leave our bins out here. And then what we're going to do is just go through number by number and start to sort. All right, I'm going to start here with 0, and I'm going to put it into my code. If the number is even, place it in bin A. Well, the number is even, so I'm going to place it directly in bin A. And I go to number 1. If the number is even, place it in bin A. Not even. Else if the number is odd, place it in bin B. Well, then that's where that goes. Then I move on to number 2. If the number is even, place it in bin A. Oh, it's even, goes in bin A. Go to number 3. If the number is even, place it in bin A, not even. Else if the number is odd, place it in bin B. And I would keep doing that. I would try it in the first if statement, place it in if it meets it. I would try it in the first if statement, doesn't meet it. Try it in the second if statement, place it. And I would keep doing that all the way until all the numbers have been tested and sorted. Hope you're doing this along with me. Not even, odd, place it in bin B. 10, is it even? Yep, place it in bin A. 11, is it even? Nope. Is it odd? Yep, place it in bin B. 12, is it even? Yep, place it in bin A. 13, is it even? Nope. Is it odd? Yep, place it in bin C. 14, even, in bin A. 15, even, nope. Odd, yep, bin B. 16, even, yep, goes to A. 17, even, nope, it's odd though, goes to B. 18, even, yep, goes to bin A. Odd, even, or 19, is it even? Nope. Is it odd? Yep, place it in bin C. So what, in bin B. So what I get is a sorting of the numbers. Bin A has all the even numbers, bin B has all the odd numbers. And I followed my algorithm, went to the first statement. If it met it, I did what it told me to do. If not, I went to the second if statement, did what it told me to do. If it didn't do that either, then I had something to do with that as well. All right, so we're going to leave this off to the side. And we're going to take out another set of numbers. And this time, also on pink paper. We're going to look at this same sort of sorting algorithm, but it's going to be slightly different this time. So I'm going to put these numbers up right up here. And I'm going to write the if statements that we're going to look at this time. So this time, my if statements are if the number is odd, place in bin B. Else if the number is even, place in bin A. Else, place in bin C. So that actually might sound a lot like we did last time. But if you take a look at the way I wrote it last time, I had you checking to see if the number was even first before you placed it in bin A, and then to check if it's odd. This time I'm having you check if it's odd first and then even. And we're going to see, does it make a difference in the way this sorts in the end? All right, so now that we're pros at this, we can go a little bit faster through it. So I'm going to leave this up like that. And we're going to start our sorting. We're going to start with the number 0 again. If the number is odd, place it in bin B, not odd. Else, if it's even, place in bin A. Oh, yep, there it goes. All right, then we move to number 1. If the number is odd, place it in bin B. Okay. We move to number 2. If the number is odd, we're going to place it in bin B, not odd. Else, if the number is even, place it in bin A. Oh, there it goes. 3. Is the number odd? Yes, place it in bin B. 4. Is the number odd? Nope. Is it even? Place it in bin A. 5. Is the number odd? Place it in bin B. Number 6. Is the number odd? Nope. Is it even? Yep, place it in bin A. And I can do the same sort of sorting with all of these numbers. 8's not odd, it's even, though, place it in bin A. And I would keep going until all of these numbers are similarly sorted, not odd, even, bin A, odd, straight to bin B. 12 is not odd, but it's even, goes in bin A. 13, it's odd, goes directly to bin B. 14, not odd, but even, goes to bin A. 15, odd, straight to bin B. 16, is it odd? Nope, but is it even? Yep, goes to bin A. 17 is odd, 18 is not odd, it's even, goes to bin A, and 19 goes directly to bin B. So let's take a look at these results. When I sorted by even, odd first and then even, I ended up with all of the even numbers in bin B and all of the odd, in bin A, and all of the odd numbers in bin B. When I sorted with the even numbers first and then the odd, I ended up with all of the even numbers in bin A and all of the odd numbers in bin B. So I actually ended up with the same sorting. So they sorted actually in a different order if you were paying attention to order, but ultimately the end product of those nested if statements were the same for both of those algorithms. The question is, does that always happen? And so we're going to try one more example of sorting these numbers, and we're going to try it with a different set of nested if statements. But before I move on to that, I wanted to see if anybody has any questions. All right, so again, we'll do this a little bit more quickly because you guys are pros. I've got different colors out this time. Same idea though. This time we're going to sort a little bit differently. We're going to say if the number is divisible by 2, place in bin A. Else if the number is divisible by 3, place in bin B. Else, place in C. All right, so this is going to be our sorting algorithm this time. We're going to go through the 20 numbers again in order, starting with 0. And we're going to go in order through these if statements. So I look at 0. Is 0 divisible by 2? Yes, 0 is divisible by everything except itself. So it goes directly in bin A. And I take number 1. Is it divisible by 2? No. Okay, I move to the second. Else if. Is it divisible by 3? No. Else, place it in bin C. Is 2 divisible by 2? Yes, goes directly to bin A. Is 3 divisible by 2? No. Is it divisible by 3? Yes, it goes in bin B. 4. Is 4 divisible by 2? Yes, it goes in bin A. 5. Is 5 divisible by 2? Nope. Is it divisible by 3? Nope. Goes in bin C. 6. Is it divisible by 2? Yes, it goes in bin A. 7. Divisible by 2? Nope. Divisible by 3? Nope. Goes to C. 8 divisible by 2, bin A. 9 divisible by 2, nope. Divisible by 3, goes to bin B. 10, find 10. Go to 11, we'll find it. 11 divisible by 2, nope. Divisible by 3, nope. Goes to bin C. 12 divisible by 2, yep. 13 divisible by 2, nope. Divisible by 3, goes to bin C. 14 divisible by 2, yep. 15 divisible by 2, no. Divisible by 3, yep. Goes in bin B. 16 divisible by 2, yep. Goes directly to bin A. 17 divisible by 2, no. Divisible by 3, goes to bin C. Divisible by 18 divisible by 2, goes to bin A. 19 divisible by 2, no. Divisible by 3, nope. Goes to bin C. And I told you we'd find 10, and here's 10. Is 10 divisible by 2? Yes, it goes directly into bin A. So I end up with a series of numbers that have been sorted. Once again, all the even ones have been placed in bin A. And I have 3, 9, and 15 in bin C. And then I have 1, 11, 19. I have a bunch of them in bin C. So different sorting algorithm, different sorting results, but everybody's in its own little bin. All right, so we're going to put this aside. And we're going to do one more before we look at these results. And again, this one's going to be the orange ones. We just looked at before because it's going to be something similar. Now remember, we were looking at divisible by 2 and then divisible by 3 last time. So we're going to do exactly the same ones. This time though, we're going to ask if the number is divisible by 3 first. If the number is divisible by 3, we're going to place it in bin B. Else, if the number is divisible by 2, we're going to place in bin A. And then else, not divisible by either one, we're going to place it in bin C. And again, the difference here between what we did last time and what we're doing this time is this time we're looking if it's divisible by 3 first. Last time we looked if it was divisible by 2 first. Same numbers there. So here we go. And we're going to do this a little bit faster. All right, 0. Is it divisible by 3? Yes, it goes in bin B. 1. Is it divisible by 3? No. Divisible by 2? No. Goes to C. 2. Divisible by 3? No. Divisible by 2? Yes, goes in A. 3. Divisible by 3 goes to B. 4. Divisible by 3? No. Divisible by 2? Yes, goes directly to A. And we can keep doing this and sort all of these numbers into their correct bins by trying to figure out, first, is it divisible by 3? Second, is it divisible by 2? And we would go all of this way, put 11 in bin C, 12 is divisible by 3, it goes in B, 13 is not divisible by 3 or 2, goes to C, 14 goes to A, 15 goes to B, 16 goes to A. Oops, you guys can't see that. I just don't put it in front of you. 17, not divisible by either one. 18 goes in bin, divisible by 3 goes in bin B, and then 19 goes in bin C. So here we have our results for looking at divisible by 3 first, and then 2, and here we had our results for looking at divisible by 2 first, and then 3. And if we look at these results, bin C, not divisible by 3 or 2, is the same values in for each case with bin C. But something interesting happened in bins A and B. When I looked if it was divisible by 3 first, I had 0, 3, 6, 9, 12, 15, and 18 in bin B. But when I looked if it was divisible by 2 first, I ended up with just 3, 9, and 15. So different sorting based on different orders. What's the difference between the two cases? The first case, I looked at odd and even, and I ended up with the same sorting. This time I looked at divisible by 2 and divisible by 3, and I ended up with different sortings for different orders. The difference is the even and the odd were mutually exclusive. There are no numbers that meet both of that criteria. So when I sorted that way, I was able to get two distinct sets that didn't overlap at all. When I changed that to look at divisible by 2 and divisible by 3, I actually had some numbers that met both of those. 6, for example, 12, and 18. So if I asked divisible by 2 first, it ended up in one bin. If I asked divisible by 3 first, it ended up in the other bin. And it makes a difference. It made a decision based on the algorithm that I was asking it to use, and it sorted accordingly. So I would have to decide beforehand how I wanted to sort that. Do you have any questions? I know that was kind of fast, but do you have any questions about if statements, nesting them, and decision making with Boolean operators? Okay, then what I am going to do is share with you a website for you to go to. And what we're going to do is go to that website, and we're going to use what we learned about if statements to take a look at some programming of Boolean gates, not, and or. So in the chat right now, I put a website, and you can click on it, and you should be able to go directly to that website. And I'm going to share my screen. This is what you should see when you go to that website. And this is an exercise, and you have access to this exercise just by coming to this website. So make sure you save it somewhere, because we won't get all the way through it today. And basically it's an API, or it's just a little set of functions that we can use in order to program logic gates, AND gates, NOT gates, and OR gates. And so before we go any further, I just kind of want to highlight a couple of things here. The first thing is what some of these symbols mean. So get A. Get A is what you use when you just want to get the value of A that you're putting into the program. Similarly, get B simply takes the value of B, and those are set by the user. Output tells you what output to print or to execute. So let's scroll down a little bit here. And this very first task is to implement a NOT gate using an if statement. So in the corner, it says A and not A. You'll see the little truth table that we had gone over before. NOT gates, remember, just changed the truth value of an input. So we have A and not A. And then we have a little coding exercise right here. Now this is not the correct code for a NOT gate, but I do want to show you how it works. So what you do is you put in a value for A in this tester, and then you click the execute button. And in the yellow box on the side, you will get the output that your program tells it to do. So again, if I put in 0, I got a 0 out. If I put in a 1 here, I get a 1 out. Now that's not a NOT gate. So I don't want a 1 to output a 1 if I have an out gate. I want it, a NOT gate, I want it to output a 0. So then I come over to the little code here in the side. And let's take a look at what this code says. It says if get A equals 0. So that's our Boolean expression. This double equal sign is looking for a truth. Output 0. Else, which means get A is not 0, so it's got to be 1. Output 1. So let me put a 0 in here. And let's go back up to line 1. If get A equals 0, well, now my A does equal 0. Output 0. So if I execute this, I should be able to get a 0. That's what it's telling it to do. Just because I want it to be a NOT gate doesn't mean it's actually doing it right now. So according to the truth table, when A is 0, I want it to output a 1. So I can make that happen just by changing the 0 on line 2 to a 1. Now if I put in a 0 and I hit execute, it gives me a 1. So now it is nodding is not really a word, negating 0 and giving me a 1. So I fixed that first part of the program. So let's go down to line 4 and figure out what to do for this else, because right now, when A is not a 1 and I execute, when A is a 1, not a 0, I get a 1, and that's not a NOT gate. So I come over here. If A equals 0, output 1. So that applies not to the 0 to output a 1. Else. Now this else means, what do I do if A is not 0? Well, if A is not 0, A is 1. And I want it to output a 0. So I can fix that right here by changing that output to 0. And then let's try it. And it did. It gave me a 0. So I think I have fixed this program to be a NOT gate. Let's just double check. I want to make, when I input a 0, I get a 1. When I input a 1, I get a 0. Those are the only 2 cases in the truth table. And so this indeed is now a NOT gate. Does anybody have any questions about that? You can put that in the chat. All right, I only have a couple minutes left, so I want to scroll down a little bit and I want to show you what else is on this page. Implementing and using the and table over here. So this is the and truth table. This time, what I have to do, and we won't have time to go over it, but again, you'll have access to this website, so you can certainly try it. I want to make sure that I can input a 1 and a 1 here and get a 1 out. So I want to make sure that the bottom line of the table is the only one that executes a 1. So right now, this is the same kind of filler program that we had up at the top. And we were able to fix that one to go directly to a NOT gate. But I can tell you that this one is going to have to also look at get B. So you'll have to have additional statements, not only what happens when A is 0, but what happens when A is 0 and B is 1. So that's where your nested if statement comes in. And like I said, you'll have access to this. It's something that you can work on. You've learned about Boolean algebra tonight. You've learned about Boolean operators tonight. You've learned about the truth tables for those. You've also learned about the nested if statements and the ordering, how ordering matters in the nested if statements. And this is a program that will allow you to take those ideas and actually code Boolean operators in JavaScript. So any questions about any of that? Nobody has any questions? All right. So I'll stop sharing now, and I will actually pin myself back. All right. So again, this is the third session of this high school educator training. The first night we started to talk about algorithms, and we looked at optimization algorithms for the traveling salesman problem as it applied to a humanitarian issue. Humanitarian issue. Yesterday, we branched out into physics a little bit, and we built our own simple pendulums, and we did an experiment actually to see how the period of a pendulum varied with string length. We did some trigonometry with that. Today we branched into computer programming. We circled back around to algorithms, extended it a little bit more into nested if statements, and the Boolean operators of not, and or. So tomorrow we'll look at cryptography. And so I invite you to come back and join that session as well. We'll be looking at various ciphers and logical places. So I hope you enjoy the rest of the workshop. Hope this was useful. Thank you, Julie. I saw that you wrote that it was. And I hope it was useful. I hope you can use it in your classrooms soon. So thank you, everybody.
Thanks, Christine. You can go ahead and end the webinar for all.
Okay, great. Thanks.
See you tomorrow.
Bye.